Well, hello again. Here's the next step in our understanding of what images look like when you look into curved mirrors. So these, again, are spherical mirrors. So imagine we've silvered like a sphere, the inside or the outside. Now, the concave mirrors is like silvering the inside of a sphere. Okay, so we found all kinds of interesting things there, like the images could be bigger or smaller. Some were real, some were virtual. Sometimes you didn't get an image at all. But this time we're going to be looking at convex mirrors. So what I have here, I have an object, but what it's in front of is a mirror that bulges out in the middle. Okay, so kind of like the outside of a sphere. My drawings don't show a perfectly accurate sphere, but this will work pretty well. There's a lot of things that are very similar about this, but the way that the light rays will bounce off of a sphere on the outside have to be drawn with a slightly tweaked description. So what I have is this exact same page we used for the concave mirrors, but I've got some words that are in parentheses that are best used if you are using a convex mirror. So we still have some of the same basic things. So for example, we have the principal plane, which is kind of like the diameter of the sphere you're dealing with. Sorry, this is the principal axis, PA. I may have said principal plane. Principal plane is actually a thing. I didn't name it for you before. It's like where the very center of the mirror goes down. So this is like the principal plane. But what's different about this is the focal point right here, it's like on the wrong side of the mirror. Remember back here, there's nothing really there. The mirrored surface is on the front all over here. So this is all your, I'll write it up here, real stuff. Anything back here is completely virtual. A mirage, if you will. So when light bounces off of a mirror like this, it spreads out. Fancy physics word is it diverges. And in diverging, all these different lines of sight from people looking at the mirror will look at the mirror as though all the light was coming from this point here, a virtual focal point on the wrong side. Okay, so important to remember that. That's why I have to tweak some of the language in the rules for how to draw the rays. But other than that, it's just drawing a few of the light rays. Of the millions that we could draw, we draw a handful of them. Maybe I'll draw a couple extra today, just to help clarify that these are not the only rays we could draw. And I'm going to use the same kind of color convention I used just for consistency. So the first rule for how these light rays bounce off is that if an incident ray comes in parallel to the principal axis, it will always reflect through the focal point. But because the focal point is on the wrong side, it can't reflect through there, and there is no focal point over here. It reflects in a direction that seems to come through the focal point. So here is the light ray that's the incident ray. The phrase we use is it's incident upon the mirror at that location. And then its reflection, it bounces off like this. You can imagine throwing a ball at a curved wall like that, and you could see it would bounce up like that. But not just any old direction. You put your ruler on the focal point and on the light ray, right where it meets the mirror. And then, now you don't draw it back here. You draw it like that. That's what the real light is doing. If we could do this with a red laser, it would look just like that. Okay? And then the second rule, this one's a little tougher, because it says if a light ray is heading to the mirror and it goes to the focal point on the way there, it will come back off the mirror parallel to the principal axis. Well, obviously, it can't go through the focal point on the way to the mirror because the focal point's on the wrong side. So we throw the word would if it would go through the focal point, like it's heading there. So this is why you have to have watch somebody doing this, because if you look at this after the fact, if I just took a picture of this when we were all done and you looked at the picture, I don't think you would understand why any of these are being drawn the way they are. You see how I've got a ray that I'm going to draw and it's heading right to this focal point, but I never make it there because I have to stop when I hit the mirror. This is what the real light does. So it's heading there, but before it gets to the focal point, it reflects, and this is the one that reflects parallel to the principal axis. Another good reason to use this clear ruler is you can kind of make sure you're parallel to the principal axis. I'm a little bent here, so I'm going to, do it like that. You don't have to be super precise, but it's kind of nice too. And then I'm going to skip the third one. I will mention there is a center of curvature. So 1, 2, 3, 4, 5, 6. My focal length here in this one is 6, not 5 as it was in the first concave mirrors. So 6 more, 1, 2, 3, 4, 5, 6. That makes 12. That is where the center of curvature would be. This is the ray that if I would draw it, it would be going directly there and it would bounce directly off. It's kind of a convenient one to draw. I think I'll draw the last one, and I'm going to get my brown pen so I can stick with that same convention. So this is a ray that is heading right to the center of the mirror. So it heads right where the principal axis and the mirror kind of coincide. So it's heading that way. And I just really like this one because it feels just like it's hitting a flat wall, like a plane mirror. And it will reflect off at the exact same angle. So if you just count squares, you don't really need to look at anything else. 1, 2, 3, 4, 5 above the principal axis means it would reflect 5 below, right through that dot right there. So we can draw it this way. And it goes right there. Okay, now, remember one of the basic ideas is that you've got a bunch of people looking at this mirror with different lines of sight. Everybody has to see the same image, even though they're sighting along a different place, wherever these reflections seem to be coming from. Now, they're not actually meeting anywhere on the real side, but if we extend them back, and remember the convention is to extend them back with dashed lines, because any virtual stuff, we don't want to make it look like it's real, so that's why we use these dashed lines. And we're just going to extend it. Now be careful you don't extend the wrong ones. They have to be the reflections. That's why I put these little arrowheads going towards or away from the mirror. Then it's not ambiguous, like, wait, is this going towards or away? So everything's got to be heading away from the mirror, and then you extend it back. And I'm not extending these as though the real light is going this way. This is just what our brain does subconsciously when it sees light rays hitting it. It naturally extends it back and just says to itself, okay, self, I guess that's where the light's coming from. Even though we know on a very cognitive level it's not. So there's the point right there where all of these rays seem to be coming from. So I draw a little dashed arrowhead. That, oh gosh, that's hard to see. I'm going to write it this way. That is my image. I'm circling this so in case somebody looks at this later, they're not like, wait, I'm missing something. The image is right there. Okay, tiny little guy. So using the lost method, I'm not going to write this because I don't have much room. The location, we would just count on the back side of the mirror. How many squares? 1, 2, 3, 4, a little more than 4, maybe 4.2 or 4.3. And that's going to be a negative. The orientation, it's upright. Remember, every virtual image is also upright, which tells us that the type is virtual. What else tells us it's virtual is that it's on the wrong side of the mirror. And the size. So this is just about, I don't know, a little over 1.5. So maybe 1.6 or 1.7 centimeters if we're using these squares as centimeters, which... sorry, my recorder kind of glitched there for a second. I had actually recorded about 5 more minutes that was lost, so I'm going to do it again. I was wanting to do the math for this one and not make a new video for that like I did for the concave mirrors, because I think the math is so similar that I don't think we need to do like a separate video for that. So we just found what the image looks like with a convex mirror. It's always going to be smaller. It's always going to be virtual and upright. Okay. That means it's on the wrong side of the mirror. So there's some conventions, we call them conventions, remember, that you need to know. And here's the main one. For this convex mirror, we have to treat the focal length as a negative number. Again, this is all based in geometry, which I'm not going to try to explain to you. I think it's a bit much. But the brilliant math people that worked this out said, oh, these equations can work for both concave and convex. As long as we use a negative sign, it'll work out perfectly. So when we count the squares to the focal point, which is 1, 2, 3, 4, 5, 6, we have to call that a -6 focal length. Okay. But other than that, like, the equations are the same. Here are the equations that we use for the concave mirrors. We're going to use the same ones. These are identical equations, just written in slightly different form. I will almost always have you use this one just because I typically ask what is the image distance, and then this one, what is the image height. Okay, so I'm going to copy that down first. So image distance, you take the inverse of the focal length minus the inverse of the object's distance from the mirror. Remember, when we measure these distances, we're measuring along the principal axis, and then we have to invert that. Okay, if you're not sure like where this equation comes from or how it looks like the other one, have me show you that, or have, find a math major, as one of my teachers used to tell me. So I'm going to plug the numbers in. So I just measured the focal length. Again, because it's a virtual focal point, I have to call it a -6. I'm not putting the units in, again, just for space to avoid clutter, but I'll put them in when we're done. The object's distance, I just have to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I did that really fast. You can trust me. And then I grab a calculator, and I'm going to punch it in. So this is -6. Actually, I'm going to open a parenthesis. -6, invert, minus 13, invert. Close the parentheses, and then invert. So my screen looks just like my page here. Enter. And if you can't see it there, it says -4.1. EI. -4.1. What does that tell us? It tells us negative means it's a virtual image. It's on the wrong side of the mirror, okay? And that bears out with what we saw from our ray diagram. 4.1 tells us how far from the center of the mirror. So about 1, 2, 3, 4. We got a little over 4 when we did it with our ray diagram. Very good match. Okay, now we're figuring out how tall the image is. This equation comes, remember, with a negative sign built in, and then this, the rest of the equation. That's just right on the reference page that you have. So the object's height, I have to go over here and count. 1, 2, 3, 4, 5. So that's about 5 centimeters tall. The image distance, use the math answer to the image distance, not what we estimated from the diagram that we drew. So that's a -4.1. And then the object's distance, again, was 13. We measured that earlier. Now notice here with two negative signs, they can become positive since we're multiplying. And then, again, we're going to punch this into the calculator. So, we got a glare there. Let's get the glare off. So, I'm not using those negative signs because they can. So, this is 5 times 4.1 and divided by 13 gives us 1.57. I'm going to round it to 1.6. Put my units on now that I'm done. And, again, a very good match for what we got on the figure, which was somewhere about halfway between 1 and 2. Couldn't be a whole lot better. Don't expect an exact match, remember. Okay? So, the beauty of these convex mirrors is that they almost always are the same. You're always going to get a similar kind of diagram. You won't have the variety like we have with the concave. And the math will always come out the same way. As long as you remember to use a negative sign on your focal length, it's going to be great. You'll get a negative here, and you'll get a positive there. Okay? Virtual and upright. All right. I think I'm going to call it quits there. We've gone on, we're approaching 15 minutes. But everything you needed to know about convex mirrors, all wrapped into a tidy package. So if you need help, as always, get some help from me. Thanks for watching. Certainly they're not. They're